Hey guys, now we're on the last topic of these four little mini lectures that I'm sending you for your viewing pleasure, which is about, ostensibly, it's about the title there, Rational Inequalities and Applications. Again, I'm going to say, look, a lot of the solutions or the type of things they're showing us how to do by hand, we'd be better off doing with a computer, doing with the appropriate technology. But there also is a section at the end of this little section 4.3 where they introduce some terminology that's pretty huge in the sciences. And so I just, if nothing else, I want you to know about these sort of ways of referring to the ways physical quantities can vary with respect to one another. So let's get started. I'm going to put the textbook on the screen. The section is about solving inequalities and equalities, and there's a difference between solving equalities and solving inequalities. So I think the first example they're giving here, right there, is an equality, but then they ask us to look at the same thing as an inequality and figure out what's the deal. Let's just walk through their solution here. They first just write down the equality. What is this process to go from this step to this step? You see that they're just clearing the denominator, multiplying both sides by x minus 1. Looks like they're multiplying by 2 times x minus 1. I can see why they did that. I would probably have done that in 2 steps, but there's sort of 2 clearings getting done by that. One is to kill off that 1/2 that's on the x, and the other is to knock out the x minus 1 that's down below. All right, so if you do both of those, multiply by 2 and multiply by x minus 1, well, on the left, you see that, well, that's a weird way for it to highlight it. That polynomial is just the double of the one in the numerator on the left side. And this polynomial, x squared minus 3x plus 2, what they have done is expanded out 1/2 x minus 1 times 2 times x minus 1. The 2 really cancels the 1/2 and makes this into x minus 2 times x minus 1, which, if you FOIL rule it, you get that thing. Then what? Well, this is the way you normally solve a quadratic thing, an equation between 2 polynomials anyway. It's you move everything to one side, and that allows you to use factoring to find solutions. So just subtracting x squared, adding 3x, and subtracting 2 from both sides of the equation, and then factoring. And when you get the linear factors, fortunately that cubic polynomial that you end up with factors completely into linear bits. The zeros are 0 from the x, negative 1/2 from the 2x plus 1, and 1 from the x minus 1. So what's interesting about this, I think, is that when you look at the solution x equals 1, that doesn't even work in the original equation. Go back to the original equation and notice that when x is equal to 1, we've got division by 0 down in the bottom of the left side. So we've got undefined is equal to negative 1/2. And those are never going to be equal to each other. You can't compute anything for the left side. That's what's called an extraneous solution, and that one's actually very predictable. How did we end up with 1 as an extraneous solution? When we did this multiplying to clear the fractions, we multiplied by x minus 1, right? And that wouldn't be valid if x was 0. So honestly, what I would prefer to do in this string of algebra is to go ahead and write the first line and the second line, but next to the second line, write in assuming x is not equal to 1. Then you can carry that assumption with you and realize, of course, you're going to have a extraneous solution. They make a good point that about inequalities. When you work with inequalities, it's tempting to do the same thing. Here's the problem. The thing that we multiplied both sides by can be negative. I mean, we just noticed it could be 0, which is bad enough, but half the time it's positive and half the time it's negative. And when you have an inequality and you multiply both sides by a negative, it changes the direction. So we either have to keep track of the two sides of the thing, or we have to do something else. Let me suggest this something else. Let's go into Desmos, and we will plot that rational expression. Wait. What was the rational pair of rational things that I had on there? The first one was x to the third minus 2x plus 1. That all is in the numerator, and divided by x minus 1. Well, it's not all that wild looking. It just looks like a parabola, doesn't it? I guess it's when x is 1, we must have a undefined moment in there, a place where the graph is, yeah, see, it's got a hole in it. Well, if I can just hold it on that spot, which I don't seem to be, there it is. You see there's a hole in the graph there. But other than that, it looks like a parabola. The other graph is 1/2 of x minus 1. Obviously, that's a line, and we are asking the question in this thing of when is the rational function bigger than the line? You can zoom in on this a little bit and see where is the rational function, the green graph, bigger than the purple line. And it's, well, starting at 0 and heading to the right, and wherever that point of intersection is. Oh, well, that comes from a factorization we saw before. So that factorization lets us figure out where the sort of important points are, where these guys cross over one another. So at -1/2 we cross over each other, and at 0 we cross over each other. Your bigger, I guess I should write this down then. From the picture you can tell that let's see, minus infinity up to -1/2, and it said greater than or equal, right? So I want to include that point -1/2, and then union from 0 to plus infinity, also including the 0 because it was a greater than or equal. Of course, if it had less than, then we would just kind of invert this and take the middle part between -1/2 and 0. So you see how using the graph can really speed this process up. All right. What remains to be done here is look at definition 4.5 in the text. So that's one of those things in a big gray box. It's a little bit way down the ways in this thing. Kind of farther than I expected down the ways. There it is. This is the terminology I was referring to when I kind of introduced this video. So whenever you have a couple of variables around, and these should be like physical quantities you're thinking about, you say that y varies directly with, or the other terminology is directly proportional to x, means that there's some constant where y just looks like that constant times x. So that little line right there is the same thing as the words y varies directly with x, or y is directly proportional to x. Now, it's less common today, but you may still see this kind of thing written using a rather strange looking symbol. It's like an 8 on its side with a part of it open. So y, and this thing is read is proportional to, so you see y is proportional to x when you that's how you read that little piece of notation. And it means just what it said in the book there, that if you want to figure out y from x, you can just multiply by some number, some constant times x. Y is a constant times x. And This is the constant of proportionality. A lot of the laws of physics used to be written in this kind of language. They'd say, force is proportional to displacement, or pressure is proportional to, well, actually that one's, pressure is proportional to temperature. But it just means you can find a constant, and then that's how people get these constants named after themselves, right? They define some physical law in terms of proportionality, and then the constant becomes, Avogadro's number, or Boltzmann's constant, or there's lots of examples of this in the language of physics. All right, so back to the text. That's direct proportionality we just mentioned. There's also inverse proportionality, which means there's kind of a seesaw between the two things. As one goes up, the other goes down, and vice versa. And, well, you can see on the screen what that means. Again, there's a constant involved, but now y is proportional. Okay. Stupid definition thing keeps happening to me. It just doesn't want me to highlight something that involves a fraction, so I'm going to have to stop trying. Anyway, y is proportional to some constant and divided by x. There's also a notion, this is less common, but sometimes you can be proportional to two different things, meaning you're proportional to the product of those two things, and that's called joint proportionality. So z varies jointly with x and y if there's a constant k, so that z equals k times the product xy. So let's look at some. They've got examples here in 4.3.6. I want to switch to the DocCam and show you those examples in that setting, because I want to write on the screen, and I haven't figured out how to write on my PDF yet. So you see all these things that have people's names associated. Boyle and Hooke and Ohm, these are famous. Every one of them's an English mathematician, I think. I'm not sure about Ohm. That sounds like a German name. Anyway, Hooke realized that if you had a spring, when you think about a spring, like one end of the spring is embedded in something. It's got a springy coil thing, and then there's a place where you can grab hold of it and pull. And the amount of force you apply here tells you how much the spring will stretch. So that's a direct proportionality. You pull on it twice as hard, you'll get it to go twice as far out. So the way you read this, the force F exerted on a spring is directly proportional to, I've left out the word to there, the extension x of the spring. That means that F is equal to k times x. If we're calling the extension x and F is the force, that k is called the spring constant, and it differs based on what kind of spring you've got, how big it is, what material it's made out of, but it's actually very computable. And it depends on what units you use. If you use newtons for force and inches for x, you're going to have some strange spring constants. But if you use pounds and inches, that's a normal, English system spring constant. I guess newtons and centimeters might be the equivalent metric there. All right, Boyle's law. Boyle was one of these people at the beginning of the Industrial Revolution who worked on understanding how thermodynamics plays, and it's all about, it was all about steam power at the time. So they were treating steam as an ideal gas. It isn't, but it can be treated that way a little bit. It relates pressure and volume. Okay, and you probably know this, that if you push down on some gas, if you try to compress it into a smaller volume, the pressure on it goes up. This is what happens when you push on the handle of your bicycle pump, and it pressurizes the air and squeezes it into your tire. So you're changing the volume and making pressure go up. All right, but the proportionality there is an inverse one. The more you change the volume, you make the volume small, it makes the pressure big. You see how that's inverse proportionality? So writing this one as a physical law, it's the pressure. I could say this is proportional to 1 over V, or that would be how Boyle probably would have expressed it. In modern stuff, we would say P is equal to a constant divided by V. And now that constant has to do with the physics of the gas you're using. This one is too easy. It's the volume of a cone, and it varies jointly with the height and with the square of the radius of the base. In fact, the volume for a cone is, let's see, 1/3 of pi r squared h, if my memory serves. But you see how r squared comes into it? So we're proportional to the square of the radius, but also proportional to the height. Make the cone taller, keeping the radius fixed, you're going to get more volume. Make the radius change while the height is fixed, you're still going to get more volume. It varies in the same direction. And then Ohm's law, that's a law from electricity. There's both an AC and a DC version of it. I think we're thinking about the DC version of it here, where the current, the amount of juice that flows through a conductor between 2 points, well, it's directly proportional to voltage. That makes sense. You probably know that you can touch both of the terminals in your car battery and not die. But if you do that, to a 240 volt outlet in your house, well, you might not die then either, but it'll hurt like heck. It's bad. I've done that. I actually once exploded a screwdriver by doing that. It was really, really fun to have like the end of a screwdriver turn into a molten gas, a plasma, right in front of my face. I have a little scar over here from that event. Anyway, so voltage makes more juice flow, but also resistance has an effect. And if the conductor you're talking about is something like it's a poor conductor, then it has a high resistance, and that means the juice that flows, the amount of electrons going down the wire at any, you want to sort of imagine it as a rate of flow of electricity. That's what current is. Anyway, that rate reduces if you've got a high resistance. If you have a high enough resistance, it can almost throttle off the flow of electricity, which is kind of what happens in an old-fashioned light bulb. There's a wire that's made out of tungsten in there. It has a very high resistance. You pass 100 volts through it, or 120 volts through it, and it gets so hot that it glows. And it's getting hot because it's got a huge resistance, and it's a really inefficient way to make light, but you're basically creating light off of the lost energy through the modern light bulbs are much more efficient with LEDs and stuff. Anyway, what is Ohm's law telling us? That the current is normally called I, and it is directly proportional to voltage and inversely proportional to resistance. The units on voltage and resistance are always chosen so that this is the proportionality constant is actually a 1 here. So if you use amps for current and volts and ohms for these two things respectively, that'll just be equals. And that's actually sort of common in physical situations. They'll choose the units in such a way that fundamental relationships like this don't really need the constant anymore. There's one last one of these. It's a beauty. It's Newton's law, the law of universal gravitation, which, let's read it. Suppose two objects, one of mass little m and one of mass capital M, are positioned so that the distance between their centers of mass is r. The gravitational force exerted on the two objects varies directly with the product of the two masses and inversely with the square of the distance between their centers of mass. So directly with their masses, that's actually jointly with their masses, looks like that, and inversely with the square. This is one of a whole family of laws that are called inverse square laws. So this is a force. Now, unfortunately, the units of mass and distance don't work out so that this just is equal. So what we actually have is a proportionality constant that is called capital G. So if you've ever seen that formula written down in a physics class, it's really just saying you can increase the force by making either one of the masses bigger, or you can increase the force by making the square of the radius smaller. The closer you bring the two things together, the more force of attraction there is. I haven't never seen this, but I'm told that some things, even man-made things, are heavy enough that you can detect this force between them. If you bring two oil tankers next to each other, like a foot apart, they will just pull in and they will suck together. It's not a very strong force even between things of that size, but it does become quite a strong force when little m is the mass of the Earth and big M is the mass of the Sun. It takes quite a lot of force to maintain us in our orbit. Anyway, that's it for this little section 4.3, and that's also the end of these videos I'm producing for you guys. So I'm going to be sad to be down in Florida and missing class with you. I'm honest about that. I've been really enjoying you guys. Our pre-calculus class is one of the more fun ones I've had. So anyway, have a great spring break, and I'll see you when we get back. I think I've included it in my email, but there's also some final book homework to do and a quiz when we get back, so watch out for those things. All right, ciao.